welcoming Raymond from Hong Kong, and he will tell us about a nuclear norm model for multi-frame super resolution image reconstruction.
Thank you, Irene. Yeah. So before I start, I would like to thank the organizer for allowing me to give a talk here. So today I will talk about this nuclear norm model for multi-frame super resolution image reconstruction. So the problem is the following one. Well, usually sometimes we call it this multi-frame super resolution image reconstruction video enhancement. So that means we are given a video, and in fact this is a video. Let me show you. So this video we download from a website by Minerva. So it's a video with 19 frames, and then the size is actually very low resolution. And then if you take out any one of the frames, then you see something like that. So let me show you the video again. So I don't believe that you can see anything from this video or from any one of this frame. But then by applying our algorithm, then you will see something like that later. So basically now you can see that so actually those are numbers, and then they are ranging from 150 all the way up to 600. Okay. So also by applying the same idea, then not only that you can improve the resolution of a video in one of the image, but you can also improve the resolution of the whole video. For example, now we have input video is a kind of low resolution video, but then now by doing the same thing, then we can improve the resolution of video. So let me show you. So this is the input video, and this is the video that we can generate from the video. So let me emphasize that we don't need anything. We just need the video and some mathematical algorithm to get the this high resolution video. So this is the aim of my talk, okay? And so this is the outline of my talk. So first I will start with the motivation. This is the ground-based astronomy that I have been doing for the past few years. So so it's a motivation of why we need this kind of algorithm. And also hopefully then I can tell you the idea of this video and still enhancement technique during this motivation. And next I will tell you the video still enhancement. That means the super resolution image reconstruction problem. So this is my second part. And then after knowing the problem, then now I will tell you the model that we use for this solving this problem. And finally, I will give you some numerical experiment. Okay. So what exactly is ground-based astronomy? So basically, so we have some images from telescope on Earth. So something like that. And then the idea is that so we have to deburr it. So this is what we can do. So after deburring it, then we get a clear, much clearer image of what we are trying to observe. Okay. So this is what we call the ground-based astronomy. In a cartoon-like image, so that means if we have an image that we want to get, so the true image, XY, the satellite, and then we try to observe it using a satellite, using a telescope on Earth, then usually that's what you see. So this is the observed image. The reason that is very blurry is because of the atmospheric turbulence. So the air is constantly moving between the satellite and the telescope. So in fact, even if you look at a one-point source, a star, very, very far away, then you will see that it's actually spread, okay, like a twinkle, twinkle little star. So, so then it's spread out. So you see that this is the point spec function of the atmospheric turbulence. So in fact, every point on the satellite, I have a pointer here. So every point on the satellite, is being burdened by this point spec function, and that's why you get this. And mathematically, so you can write it as a convolution equation. So F is the true image, and then you have the convolution kernel, and then you get the this observed image under some unknown noise. Okay. So in the case where you have a spatially invariant kernel, then you can write it as, of course, like this equation, where so F here is the vector, and K here is the box-Topis block matrix. And then of course, now if you know K, then of course it's easy to solve. It's a standard Topis least square problem. In fact, I have a book on this. There are many fast methods for solving it. But of course, for our problem here, the problem is that so this K is the atmospheric turbulence. We cannot, we don't know the K, right? So there are other ways to try to estimate the K. For example, using what we call the artificial guide star. So the idea is that you shoot a laser into the atmosphere near the satellite, and then you burn a point in the atmosphere, and then you observe how this point is spread. So you get the point spread function near the satellite, then you get the K. And then once you get the K, then of course you can use, as I said here, so you can use this standard techniques for solving Topic matrix equations to do it. In fact, we done it almost a quarter of a century ago. Okay. Now, but today I will tell you another way to estimate the K. So the idea is this. So if a wave coming from far away, then before it hit the Earth atmosphere, it's basically a planar wave. But then just after it hit the atmosphere, then it got distorted. And the distortion, usually we denote it by phi. It's called the phase or phase error, or sometimes we call it wave front. Now, if you can measure this wave front, then the thing is easy, because if you can measure this wave front on the telescope, for example, this is a telescope aperture, okay, because you cannot observe the whole sky, okay. Then now you plug it into this formula. So you measure the phi, and then restrict it onto your telescope, take the inverse Fourier transform, and then take the absolute value square. Then you have the point spread function already. You have the point spread function, now you can deburr. Now, of course, then it seems to be an easy problem, but unfortunately, on the telescope, we have this waveform sensor. They are trying to measure the waveform, but unfortunately, they cannot measure the waveform directly. They can only measure the waveform gradient. So the x derivative of the phi and the y derivative of the phi. Now you may say that that's still easy, right? So after getting the derivative, then we just take an integration, then we get the phi again. But unfortunately, on the waveform sensor, so this waveform sensor, they are very low resolution. So in fact, the European Union is building the world's largest telescope to be online maybe 8 years from now. So even on this world to be a largest telescope, so the waveform sensor, the resolution is 88 by 88. Only 88 by 88. Now it's not because they cannot build a higher resolution sensor. It's because there is not enough photon to collect. So that's why they have to build this very low resolution waveform sensor. So let me show you this video. So this is a true phase, but then on the telescope, basically that is what you can observe. Okay. So this is the x derivative of the phase under this low resolution waveform sensor. So then now the question becomes, okay, so if we use this low resolution waveform sensor measurement, and then we do the integration to get this phase, that phase will not be accurate. Okay, if this phase is not accurate, then you put it into the Fourier optics formula, your kernel will not be accurate. Your Burring function will not be accurate. And then you deburr the image, then your deburred image will not be accurate. So that's the problem for us, okay? So, so now the question is, how do we improve on this? So this is the physical limits we have, okay? In 8 years, actually, not now. So now this is the problem. So we can only get a low resolution waveform gradient, okay? So we want to, from this, we want to get a high resolution waveform gradient. So how do we do that? So the idea is that, so you try to observe or obtain a sequence of low resolution waveform gradient. Get a sequence of it, and then from this, then you try to do something to get a high resolution waveform gradient. Okay, and then now from this, then now you can do the integration. Hopefully, then you can get a accurate phi. Okay, from the accurate phi, of course, now you can reconstruct the accurate Burring function, point spread function. And from that, then now you can deburr your telescope image to get a clear image. So that's the plan, okay? And then, of course, it all boils down to how do you get a sequence of a low resolution waveform gradient? How do you get this? Or where do you get this? So the idea is that, so this is one idea, okay? One idea is that, so you have a low resolution waveform sensor on your telescope. Now, how do you get a sequence of low resolution waveform gradients? So the idea is that you move the telescope. Now, if you move the telescope within a short time, assuming that the phase does not change, okay, then now on the overlapping domain, then you will have a more sampling points to get possibly high resolution waveform gradient. So that's the whole idea. Okay, so this idea actually is proposed by Jeffrey and Hart in their paper. Okay, so once you use this idea, then question is okay. So this is our measurement. So this is the x direction of the waveform gradient in the low resolution, and this is the x direction of the waveform gradient in high resolution. So then now, in order to get from here to here, then all you have to do is set up the equation relating them. Okay, so what are the equations relating this measurement to the to something that you want to get? So basically, these are the equations. So let me tell you exactly what they are. So now here you have the px. So for example, this x direction waveform gradient. Okay, so this is W is your telescope aperture. So you can only observe this part of the sky. Okay, and the first time, so your motion vector. So this is actually identity. And then so you observe this part of the sky, and then you downsample it. So your M1 is identity, and then you check onto your telescope, and then you downsample it. Then you get the first measurement. Okay, and then now you started to move your telescope to M2, and then you observe the other one. Then you get another observation. Okay, so by doing that, then you have all these observation. So then that's how we relate the QI, so the measurement, to the thing that you want to get. Okay, so I should emphasize that so this R is the downsampling operator. In fact, of course, we are giving this. So actually, you can consider this R is the inverse of the upsampling operator. Okay, so how fine you want your final waveform gradient to be, then you define your R. Okay. So now once we have this equation, so let me go back. Now how do we get from Q to the P? Of course, you minimize the noise, right? So using this square. So then you get this equation here. So this is actually by Jim. So they propose this, actually this is taken up vectorization. But because this matrix is singular, so you need some kind of vectorization. So they use L2 vectorization. And later on, we propose to use the L1 vectorization. Now, in any case, so if you use these two models, the first thing you have to observe is that after you get the P, then you still have to do the integration to get the phi, right? So this is the P. So because the P and the phi, they are related by this, then you have to do least square to do the integration here. So, but then if you want to observe this, actually, so you can substitute in. Then from the measurement, you can directly compute the phi. And then you just set up the minimize the noise. Then you get L2 norm here, and then now you can directly regularize the phi, okay, using anything that you know about the phi a priori. Okay, so now I have to introduce a free model to you. So how to get the phi? So now let me show you how good this kind of high resolution idea works. Okay, so suppose now here we generate a true phi using the Kolmogorov formulation. So we generate this true phi. In fact, we generate this true phi such that the seeing condition is 45. A seeing condition is actually proportional to the wind speed. So wind speed is 45. That means actually it's a very, very fast wind speed, and people don't observe the sky under this seeing condition. So it's a bad condition. In any case, so we try this, okay? And then now we move the telescope 16 times, and then we we take the x derivative and then the y derivative. We move the telescope 16 times, and then we downsample by 4. Then we observe. Then we take this observation. So we have 16 x derivative low resolution observation and 16 y derivative low resolution observation. Now from this 32 observation, we want to get this back. So that's the problem. Of course, to do that, then of course all we have to do is to solve the three models that I have mentioned. Okay. So once you solve this free model, then you will have their respective phi, and then now you put this phi back into the this formula. Then you get their respective point-space function. Okay. Now because we also have the true phi, then of course you put the true phi here. You also have the true point-space function. Now then you can ask, okay, so how this free model compare for the PSF relative errors? So now you see that we moved the telescope 16 times. So supposedly, around the X frame or the line frame, so there are more overlapping pixels. So the errors are the smallest. Now, if you use the L2 Tikhonov vectorization, then you get actually the error is also very high. It's about 25% in the K, in the point-space function. And then you use the L1, L2 model for the P. So maybe I go back. So in case you already forgotten. So this is the L1, L2 model for the P, okay. Then you still get like a 25% error, 22. Now if you get the combined model, so you just substitute in, then you get a 5% error in the K. Now, once we know that, so this model is better, so then now you may ask, okay, now we have a better K. So how good when we use this K to deburr? So let me just show you. So here is also a simulated test. So we have the true image, we bury it with the true K. So this is the true K from this true phi. So we bury it with the true K and then we add some noise. Okay, so this is suppose what you observe on the telescope. Now, if you know the true K, then you can deburr it again, right? So if you, because now we know the true K, we can deburr it again. So if you know the true K, you deburr it, actually you see everything, almost everything. So even the fine structure of the telescope, of the satellite, you see it. But of course, in real case, we don't have the true K. That's why we need to solve the free model to get the K and then deburr this image. Now let's see, okay. So let's see if we use the Tikhonov regularization. Then you to get the K, and then use that K to deburr this image, and that is what you will get. Now you see that now basically you only see the big structure of the satellite. All the fine structure are gone. Now of course this is because the point-spread function of the actually the error is very high. Even for this one, it's also very high. So that's why even if you use this one to deburr, you still get you may be slightly better than this, but then you still don't get any fine structure. But how about using this one? This one has a very small relative error in the point-spread function. So if you use this one to deburr this image, that's what you get. So you see that all the fine detail they are coming back. Okay. So you see that this kind of idea, so high resolution image reconstruction, it can be used to obtain the point-spread function. Now, in fact, so we are working with Ronnie Ram now in Austria. So they are providing the software for this the biggest telescope from on Earth by the European Union. So actually the telescope is 40 meters in diameter. It will be 40 meters in diameter. So for such a big telescope, you don't expect them to move. Okay. So then, that means that now if we don't move the telescope, how do we get the samples or the sequence of low resolution waveform gradient? Now this is one difficulty. Another difficulty is this. So in fact, up to now, I only mentioned to you that between the telescope and the satellite, there is only one layer of air moving. But in practice, actually, there are many layers of air moving. So here, this diagram just shows 2 layers of air moving. So for each of the layer that the air is moving, then you will have their corresponding wavefront. Okay, and then so if you have L layer of air moving, then the combined wavefront is actually the summation of all these, and then you get the phase, total phase of all this. Okay, and then you have to get the burring function to deburr this image. Then basically you compute all this phi, and then you plug it in, then you get the burring function for this whole atmosphere. Okay, up. Now, so actually, this is not a difficult problem. If you have L layer of air moving, then you just set up the equation that I did before. Then you have you still have a L1, L2 problem to solve. Okay, so you just set it up. But the problem is that how about moving the telescope? Now we cannot move the telescope, but it doesn't matter. In fact, you need not move the telescope. In any case, if something is moving, that is already okay. Because here actually the air is actually moving. So we test with Ronnie. So they give us some tests. So for example, here we have 3 layers of air moving. Okay, so at time t. Okay, so the phase is like this. So you just sum this, then you get this. Now and then we assume that the air is moving like this. So for the first layer, it is moving like this. Second layer, moving like this. Third layer, is moving like this. And then we don't move the telescope now. Okay, so we just take the observation. For example, after 10 milliseconds, so this is after 5 frames. So we observe something like this. This is the x derivative of the waveform gradient. Okay, and then of course we also have the y derivative. I don't show you. And then we also take 10 frames. Okay, so this is the last frame in the y direction. Okay, so we have 20 frames like this. Now from the 20 frame, then we want to get this back. Okay, so now then, well actually, so how good this is? So I can tell you that this is the reconstructed one, and this is the true one, and the relative error is actually very small. Okay, it's 2.5%. In fact, the air condition, seeing condition, we set it even higher than before. It's 50. So even in this very worst case, you may say, so the idea still works. The idea still works. So let me summarize this part. Okay, so as a motivation, as I said. So the motivation is that so whenever you have a video, and then something that is moving, either the camera is moving, or the object itself is moving, then you can combine the information to get a high resolution of whatever you want to see. So that's the whole idea of what this motivation. Now I go into the detail of how to set up the equations in general. So basically, this super resolution image reconstruction is not new. In fact, this is what we see every day in these insect eyes. Okay, so these are the compound eyes. So they have a very small lens, but then there are many. So the whole idea is that so you have many lenses, so you get a very low resolution image from each lens. But now the question is, can you combine the information to get a high resolution of what you try to see? So in order to understand this process, so let me just illustrate this by a very simple example. So here we have 4 low resolution image. Each of them are 64 by 64. Okay, and then from this 4 low resolution image, we want to construct a high resolution image 128 by 128. It is subsampled by 2. Now, of course, these 4 low resolution images, they are not exactly the same. So this is the usually what we call the reference image. We do not move it, and this one is actually moved from this one by half a pixel to the right, and this one is half a pixel to the down, and this one is half a pixel diagonally. So actually, so these 4 images, they have independent informations. So now from this, then we want to reconstruct this. So that's the whole idea. Okay, so now in order to understand what is the process in between, then let me just show you. So suppose this is the low resolution pixel, so it's a big pixel. Okay, so from this pixel, we want to get a high resolution image, which is double the size. So that means so we want to get this pixels here, their values. Okay, A, B, C, D. So these are the high resolution pixels, and then we want to get their values. Now, what is the way? So here, you understand that. So the pixel value of the low resolution pixel actually is the sum of this or average of these all 4 pixels. So that means now from the average, so this is the given intensity of the low resolution image, and then we want to get the A, B, C, D back. Now, of course, if you only have one low resolution image, then you cannot get A, B, C, D back. But we don't have only one low resolution image, right? We have 4, and then they are placed at half a pixel apart. Yeah. So that means for the first low resolution image, you can actually get an equation relating D. So these 4 pixels added together is this value here. From the second low resolution image, then you get another equation relating D. From the third one, you get another one relating D, and then from the fourth one, you got another one relating D. So actually, if you have 4 low resolution image, you have complete information about D. If you write it out as a matrix, then you can write it out like a tensor product form. So for the first low resolution image, you can write it. So this is the high resolution image that you want to get. Now, how do we get the first lower resolution image? Actually, it's smoothed by this E. So actually, it's just averaging. So n here is the number of pixels. Okay. So actually, you see that this is very simple. So you take the x average and the y average, okay, and then you get the first lower resolution image. Oops, sorry. And then if you write this matrix as a B1, then you get this equation. Now, of course, you can do it for the second image, low resolution image, the third one, the fourth one. Then you have these 4 equations, and then you stack them up. Then you have this one. Now, the interesting thing to look here is that if you do a very simple reordering or permutation, then you can rewrite this matrix as B out equal to Q, where the B is block to bit block. Okay, so this has a very rich structure actually. Now, so that means that for this problem, actually, it's very easy to solve. Okay, so even if you have noise, then you just minimize the noise, then you solve this block to bit block matrix equation, then you get the high resolution image. Now, this is exactly when the four low resolution images are lined up exactly at half the pixel length. At half the pixel length, okay. But of course, in reality, so when you have a video, you don't expect this. You don't expect the low resolution image. They are aligned exactly at half pixel. Okay, so let me show you this video. So this video is a video of bookshelf. It has 30 frames per second. So if you just take out one frame and then zoom in maybe on this number here. Okay, that's what you see. Okay, you see nothing basically. But if you have 30 frames per second, actually you can take out 30 frames and then try to combine the information, and then then you can get something like that. So we have done this a long time ago. Okay. So, but the problem here, different from the super resolution case, is that so now here actually we use 21 frames. Now none of these 21 frames are exactly half the pixel from this original image. You don't expect this, right? So the probability that of any one of this frame is at half the pixel length from the original one or from this one. The probability is basically zero, right? So that's the problem. But it doesn't matter actually. So if they are not at half the pixel length, all you have to do is to estimate. So how far they move from your reference image. Okay, so all you have to do is to estimate this displacement. Now once you estimate this displacement, then you can set up the equation again. Then you can solve it. Okay. So now let me tell you exactly what. So suppose that these are and then we can set up the equation. So suppose these are the high resolution pixels, okay, that we want to get. And these are originally in the ideal case you want the low resolution pixels are exactly aligned with like this, okay. But of course because the video is moving, so they may be aligned like this. Okay, so that is what you can get, okay, in the video. And so these are displaced low resolution pixel, and then these are what we call the displacement errors in the x direction and in the y direction. Now the idea is that so if you can estimate this, then now you can also put the equation into a matrix form. So if you can measure the x displacement of your image in the video from the reference one, and the y displacement from the reference one, then for example from the first image. Then you can just write like a matrix equation again. So but now it's still topos, but then you have something not exactly 1/2. Okay, so you have a 1 minus this displacement. Okay, this is the x displacement, and then you have the y displacement. Then you just do the product equation, tensor product again. Then you get this equation. Now depending on how many images you have from your low resolution video, then you can stack them up again. And then you get a matrix equation. Now this matrix equation is, well, it's no longer block to bits block, and also it's no longer square, because maybe you have a 21 frames, but then you only want to do upsampling by 2. Okay, so you have more information than you need. Okay, but in that case, so you set up this equation. Okay, so this is the equation that you need to solve. Okay. Now once I hope I tell you the mathematics behind the equations. Now once we have set up the equation, now it's easy to solve. So depending on how you try to solve it. So in the following, I will tell you 3 methods of solving it. So the first one is the classical one. The second one is the time frame one that we proposed also a long time ago. But the last one is the one that I would like to tell you today. So the classical one is actually a very simple idea. So suppose you have a low resolution video like this, and then you want to get this number from the low resolution video. Okay, so but then of course in each frame, then you have a low resolution image of the numbers. Now in the classical approach, basically you can assume that so we are trying to reconstruct this high resolution image from this low resolution video, and then what is the relationship between this high resolution number and this is the low resolution numbers here. So of course once first of all, so you downsample them, right? So then you get this. So you downsample this one, then you get this. You downsample this one, then you get this. You downsample this one, then you get this. So then you have this equation. okay, with some noise, okay. So then you solve this, basically. You solve this. Now the BI, what is the BI here? So so the BI, in case you have already forgotten, the BI are this one. So these are the BI, depending on how you estimate the displacement. Then for each low resolution image from the video, you have one BI there, okay. So you have all this BI, and then now you set it up. Then now you just solve it. So this is the classical approach. So given the low resolution video, then you can get the high resolution image by solving this problem. In fact, so in the waveform reconstruction, actually exactly this is the classical approach. If you think about it, so because now we have this waveform gradient, and then from the x direction, from the y direction, and then you want to reconstruct the wavefront, and then this is the Berling matrix, and then from the observation, then you get this, and then you regularize it. So this is typically the classical approach of doing this, okay. But then there are other approach. For example, the type frame approach that I would like to tell you. So what is the type frame approach? So the idea of type frame approach is that, so suppose these are the high resolution image. Well, in case you don't know the type frame, so you can just treat it as wavelet, okay. So wavelet approach, okay. Then it's easier to understand. So in case so here, so we want to get this high resolution pixel value back, okay. But we have, for example, we have only four low resolution image, okay. So for example, now the first low resolution image, we can actually paste it like here. So then if you paste it slightly here, then you will ask, okay, so what is the relationship between this low resolution pixels value and those high resolution pixel values? What are the relationship between them? So in fact, well, all you can do is one way you can do is just to take the weighted average. So this high resolution, this low resolution rate pixel value is 1/4 of this pixel value, 1/2 of this pixel value, 1/4 of this pixel value, etc. So you do a weighting. Okay, if you understand this, then basically from the high resolution image to the low resolution image, basically you are passing the high resolution image through a filter, through this filter. Okay, which of course many people already know. Okay, but the interesting thing here is that given this filter 1, 2, 1, actually you can complete it by a type frame to get a complete type frame basis. So this type frame has actually this piecewise linear type frame. So it has a 1 low pass and 2 high pass. The two high pass are basically the first order derivative and the second order derivative. Now for each of this filter, so you construct the filter matrix. For example, this one, you construct this circular matrix. Of course, here I just tell you the 1D to avoid the complicated notation. In 2D, of course, you take the tensor product of this, and then you get the filter matrix for the low pass, and then correspondingly, you also have the high pass filter, and all of these are basically box circular box matrices. And then now, once you observe this, now then you can say that, okay, so from the from the high resolution image to the low resolution image that we observe, actually, so you just pass it through this filter, low pass filter, okay. So you just pass it through the low pass filter. So then that means so actually the low resolution image, they are just the frame net coefficient of R. Now once you notice that, then actually now you can complete the basis. So now you can complete the basis. Now you can get the piecewise linear transform, type frame transform here. So and then now you observe that actually the problem now becomes how do we find the R? So if you take the R and then take the type frame transform, then you have this vector here, but then some of the vectors are given. So they are given by the low resolution images. But some of the high resolution coefficients, they are completely missing. So if you observe this observation, then basically, so to get from the low resolution image to get back to a high resolution image, basically you are doing an imprinting here. So this is our key observation. So the key observation is that this high resolution image reconstruction basically is just a frequency domain in painting, in the type frame domain. In the type frame domain. Or just maybe I use this graph to illustrate. So in order to get back this high resolution image, so in fact you take a look at this. So if you take the type frame transform, then these low resolution image, they are given here. So your low resolution image are given here. And then all is missing is the high frequency coefficient. If you can impinge on the high frequency coefficient and then take the inverse transform, then you can get the R back. Okay. So that means the high resolution image reconstruction is the following problem. If you look at it. So in order, given the Q, how do we find the R? So given the R, then you take the transform and then you restrict into the low resolution part, then it's the Q. Now given the equation, now you want to find from the Q to the R. Now once you know this equation, now then you can set up the formula to do it. So basically now how to get the R from the Q. So you say, okay, so we take the R, we take the type frame transform, then we have the coefficients. But the coefficient we shift on the low frequency domain, then is the given low resolution image. And then we regularize this C by the L1 norm. Okay. So this type frame approach actually is very different from the classical approach, because the classical approach you use this, and our approach you will use this. Okay, so it's different. And that's actually this algorithm, the algorithm for solving this, we proposed it back in 2003. So in this paper, Shen, so we call it C square plus S square. Okay. So in fact, so this is the first iterative thresholding algorithm. Because if you look at the history, so there are of course many thresholding algorithms now. But our algorithm is the first one to propose it. Okay, so finally I get to what I try to tell you today. Okay, the low rank model for doing this. Now, the low rank model is something like this. So suppose you have a low resolution video. Okay, and then you want to these are the video, these are the images that you have. Okay, from the low resolution image video, and now you want to get a high resolution image out of it. So we don't assume that they come from one video, one image. We assume that they come from one high resolution video. So and then correspondingly, then you have a one high resolution image of this image. You have another high resolution image of this image. Okay, so basically you just downsample, then you get what you observe. Okay, so then you get an equation like this already. But now of course the next thing is so this video they are moving, so you have a motion matrix here. So the idea is that how do we relate this R1, Ri, Rm together? So by this motion matrix, okay. And then because they are all high resolution matrix images, that they define on the same size. So it's different from the classical approach. Now the question is, how do we define this mi? Okay. So let me tell you in simplest form. Okay. Otherwise, then it's very complicated. So I tell you in the 1D form, okay, so this motion matrix. So suppose this is Ri, so the ith one is just a horizontal strip of this one, the first one, okay. So and the horizontal strip is a rational number, okay, so and then we have the integral part and the fractional part. So this is the first image, but the Ri image is moved by, for example, here 3 point something. Now 3 point something, actually you can decompose it as it moved first 3 pixels away, and then now you add another half a pixel, maybe EI pixel further. Okay, but the EI pixel further actually you can approximate by interpolation. So that means actually so if your image is moved from the first one by this Li plus the EI distance, then you can decompose it into 2 processes. First you move it with integral part. Integral translation, and then you do a fractional interpolation. Now once you understand this, then actually the motion matrix can be decomposed into 2 matrices. So the first one is the integral translation. So that means you move your image Li pixels, and the S is the strip matrix. That means it's the upper it has a 1 in the upper diagonal. Okay. And then the EI, so finally then you have the fractional interpolation. So this one, which you can write it as a Topic matrix. Okay. So in fact, then now you see that so actually the motion matrix can be decomposed into 2 Topic matrices. Okay. So once you know that, then now what is the relationship between the Ri and the M and the R1? So they are given by this, okay? And then let me call this integral strip of R1 Fi. Now you see that this Fi, basically they are integral strip from each other. So there are no any more fractional strip anymore. So we decompose it out. Okay? So the remaining part, so if you look at the remaining part, this equation here, so this equation is this one, right? So if you, let me go back, sorry about that. So this is the downsampling one, so this one. So now we can replace the Ri by the Fi. Okay, so because this one, then we plug it in. Now the nice thing about this is that all the Fi, they are defined on the integral pixel, so they are no longer fractional pixels. So this is very important. Because if you restrict that all this, so this is the common area that you want to do the high resolution image reconstruction. So if you do this, and then now the thing you observe is that, so these are basically the same vector. So this vector is the same as this one. This is the same as this one, same as this one. So in the ideal case, this matrix, if you put it this matrix, then this matrix is rank 1. In the ideal case. Okay, of course there are some noise, right, in the computation, or there are some error in the interpolation. Okay, in any case, so once we know that, then now basically, so we can set up this model. So we have this equation here, error, so we minimize the noise, and then we know that this matrix is low rank, so then we minimize this. Okay, and then now once we know this form, then of course we can convexify it. Okay, and then we do this, and this one of course is the L1 L2 problem, which you can solve it very fast. Okay, so far I told you the situation in 1D case, but in 2D case it's the same. So if you have the reference image here and then the Ri is moved like this, then all you have to do is to estimate the x direction and the y direction, and then you decompose them into fractional part and the integral part, and then your matrix can be completely diagonalized, completely written like this. And then if you written like this, then now you can also factorize them into one that is a Bloch-based matrix, and the other is basically some kind of very simple diagonal, which some kind of about band matrix, okay, constant band matrix. And so basically these are very simple matrix. And then now you can do the same thing, and then you can see that this matrix, because they are all representing the same image, and then if you line them up as a vector, then it should also have low rank. And ideally they should have it should have rank 1. Okay, so then you put it like this, and then as I just said, that this is the L1 L2 problem. You can solve it easily using ADMM, or what we call the SVD thresholding algorithm. So then in this ADMM, then you have to compute a SVD of a certain matrix of this form, and the cost is very small. So N here is the number of pixels, M is the number of frames. So the frame usually you have the 20 or something like that. So this cost is very little, but the most cost is to solve an M linear system of size n by n because of this. Okay, but as I mentioned all along, so all this matrix Ci, so Ci actually is a diagonal matrix with 1 or 0. R is the downsampling matrix, Ti is the Topic matrix. So you can explore this in your linear system. Okay, so I hope I tell you the basic idea of the method. So now I give you some numerical results. So this is a bookshelf. So again, so we want to see the number. So if you only use one frame and upsample by linear, then you get this. This is a 21 frame using a TV. So this is the classical method using TV. And this is the So this is using tight frame, and this is using a nuclear norm. So the one I just proposed. And this is another image. So this is a video. Also again, so we download the video from Milan's database. Okay. So we didn't do anything. Just download this, and then this video has 19 frames, and we use all 19 frames to get the high resolution image. So let me just show it again. So if you take out one frame from this, then that's what you get. Okay, so basically you don't see anything again. So this is some kind of also a low rank approximation, different from ours. This one is the classical one, classical approach, but using a tight frame as a regularizer. And this is our tight frame, and this is our new method. So now hopefully you can see the characters here. This one also I guess Well, if you look at the video, then take it out one frame, then maybe you don't see anything again, right? So, but then after doing this, then you can basically read the characters. This is another video also from Milan database. So again, so you don't see anything, but even with the so this is the reference frames, and this one is upsampled by 2. But if you upsample by 2, basically you can see this word foot surface, but this one is not here still. But then you can upsample by 4, right? So now we upsample by 4. Then now you can see clearly the word. If you cannot see it, then let me zoom in. So this is the reference image. So this is the image taken out from the video, and then you don't see anything. Or maybe you can guess this foot, but now you can easily see that words. Okay, so this is the one that I saw at the beginning. So this is the low resolution video, and then if you take one frame out, then this is what you see. And this is the classical approach with tight frame regularizer, and this is another low rank approach, and this is our tight frame approach. This doesn't do well here. And this is the nuclear approach. Okay, so the one that we propose. And then if I zoom in, then that's what you see. And this is the classical approach with the tight frame as a regularizer. So it's also doing a good job up to 200 probably. But then they cannot see this. So here we can see 400, the 500, and the 600. I guess you have to guess. But in that case, so you can see up to 500. And we can do it for video, for color image, or color video, of course, right? So here it's the same bookshelf image, but we want to see, I think, the book here, with the book title here. Okay. So you see that the book title. So this is the reference frame, but then we can see now this is Fourier transform data image. Yeah. Now for all this, because this is only a video, so we don't know the true image, so there is no way to compare the error. So then that's why here, so we artificially construct a video ourselves. Okay, so this is the true image, and then we move the image around, and then we also change the intensity, light intensity. So you see that, so it's going from dark to bright, right? So getting dark and then getting bright. Okay, so we also do this, and then now we use this, and then we construct the image, and then we can compare now. So what is the error compared to this one? So these are the errors. So this one is 26 point something, yeah. Okay, so far what I mentioned to you is that you have a video, and then you use the video images in the video, and then you construct a high resolution image. But the whole idea actually, you can do the same thing for so that you can create a high resolution video for a low resolution video. So the whole idea is that, so given a low resolution video, you take out the frames. And then for each frame, you do something that whatever you like to do, okay? So you just upsample them. And then once you upsample them, then you put them together, then you get a high resolution video, supposedly. Depending, of course, on your method. Here. Okay, so let me show you. So this is the input video that you have seen already. So it's a low resolution. This is a classical approach using a TV as a regularizer. Now this is the simple approach, so you just do the bicubic upsampling. And finally, this is the tight frame approach, okay? So we haven't tried the nuclear alarm approach yet. So let me show you the result. So remember that we only have this video, okay, and then our algorithm. So nothing more. So hopefully you can see the difference between here, and the difference between here and here. So this upsample bicubic is well, maybe a little bit better than this one, but it's not good. Okay, so yeah. So another one. So let me just show. Sorry. So this is another one. So it's the same thing. So this is the same thing. So this is a low resolution. So you see the technical. So so here the technical they are much finer than this one. Okay. So let me conclude. So basically, I told you a new approach for video still enhancement. So basically, the whole idea is that you decompose the motion matrix into a strip matrix and a topos matrix. The strip matrix for the integral strip, and the fractional matrix for the topos matrix for the fractional strip. Now, once we have this, then we can enforce the low rank structure, and then now we can solve it using ADMM. Okay. So So before I end, so let me just make a little advertisement. So next year we will have this SIM a Pioneer Algebra conference in Hong Kong. So it's on May from 4 to 8. So this is most people know about Hong Kong or imagine what Hong Kong is. Okay, but then there are many things that hopefully will attract you to Hong Kong. So food is one thing, but we also have very beautiful beach. Okay, so like this one, almost deserted beach. Because you have to walk a long way, like an hour to there, so on this path, or you can rent a boat if you are wealthy. Okay, then you don't have to walk. But then, in case you are coming to Hong Kong, so try to visit my university. So my university is another harbor, so it's also a beautiful place. So okay, so with this, I end my talk. Thank you very much.
Questions? Maybe one quick question, yes?
How do you estimate the errors, the displacement?
Oh yeah, I didn't have time. So actually, so we
AIJ.
Epsilon ij, right?
It was slide 29.
You mean the AI? Oh, for the let me see what you trying to say.
29.
29. I'm sorry about that. Take more time. 29. Yeah. So yes, exactly. So I didn't have time to go through this. So let me just mention that. So we have two. So we have two ways to estimate it. One is the local motion estimation. We use the optical flow. But then this algorithm, we just take it from off the shelf. So we just take it from my colleagues. Okay. And then a global estimation. So basically, this is a fine approximation. So you just solve a 6x6 linear matrix. Okay, yeah. So I think it's stop.